Good morning, everyone. Yeah, I'm glad to see everyone here. Still second day, still so many audience in the room. Okay. Yeah, so I have some message from the general chair. Yeah, so I think yesterday, some of our friends, bring some food inside the room. So I think, I think today for today's session, so please try not to bring food inside the room, okay? And also please turn off your mobile phone now, okay? Because we were going to have a very impressive, inspiring talk from Professor Yao Wen Chang, okay? So good morning, my name is Dong Yi-ho. I'm the professor from the Chinese University of Hong Kong. Okay, so because I saw many new faces here, so I think I still need a introduction for Professor Yao Wen Chang, but I think most of you already know him very well. Okay, so Professor Yao Wen Chang, he received his PhD degree from the UT Austin under the supervision of Martin Wang. Okay, in 1996. Okay, and after that, currently he is a distinguished professor of National Taiwan University, and also the dean for the electrical engineering and computer science. Okay, the same in National Taiwan University. As a professor, okay, and also the former student of Professor Chang, I really admire for his outstanding performance. So let me provide you some facts. Okay, the first is about teaching. Okay, so he received 11 outstanding and excellent teaching award, okay, in National Taiwan University. You know, every year only once. Okay, so that means he already had 11 years to receive the teaching award. So professor like me and many professors here from Taiwan and several tech lead and also senior director in, for example, TSMC, Media Tech, Synopsys Academy in Taiwan. They are students. They were students of Yao Wen. Okay, yeah. So I think he really followed the guideline from the President Xie Liu. Okay, for the teaching philosophy from to instruct, to invite, and to inspire. I think he inspired several of us. Because of him, we are now in. We are now working in the EDA area. So talking about research, I think I think too many, so maybe I can make it short. I think he is the most prolific author for Design Automation Conference. So guess how much? He published 91 tech papers. Okay, yeah. So it's really remarkable, and also received the 11 best paper awards, including tech, ICT, and ICT. Okay, and he also won 23 CAD contest award. Okay, and I think so many. And so I think make it short. For service, he was the chair of, he was the president of IEEE, and also he's all friends of ISPD because he was the general chair of ISPD and also ICK. Okay. So let's welcome Professor Yao Wen Chang for the wonderful talk. Okay.
Yeah, good morning. Thank you so much for coming to Taiwan. Because Zhong Yi was my former student, so whatever he said might not be true. Okay, yeah. It's such a great pleasure to have so many good friends from afar, yeah, especially to our National Taiwan University, yeah. Okay. In this talk, I'd like to share the visual design challenges in modern heterogeneous integration. Yeah. As Zhong Yi mentioned, we have a tradition. I have to tell you something before my talk. Okay? Yeah. First of all, I would like to thank all my collaborators, yeah, including my PhD advisor, Professor Martin Wong, and also students and also friends. Yeah. They make the most contributions to this work, so they should take the most credit. Yeah. My students are very smart. Let me share you with us a story. Yeah. About 10 years ago, Martin visited Taiwan, so I asked my students to discuss with their grant advisor. Yeah. So after the discussion, I checked with my students. Well, guys, how do you feel about my advice? They replied me with smiles. Boss, well, they always call me boss in Taiwan. Okay, yeah. Boss, it seems that your advisor is much better than ours. Then I rushed to Martin for what happened. Hi Martin, how was the discussions? Martin replied with an even bigger smile. Well, Yao Wen, your students are much smarter than mine. So you know how smart my students are. Okay, yeah. I'll follow the outline: technology background, visual design challenges, solutions, concluding remarks. Yeah. By the solution here, I don't mean the challenges that I'm presenting there are well solved. Okay, yeah. So there are still many research opportunities here. Yeah. We have a few technology drivers, including the AI, high-performance computing, automotive electronics, 5G, 6G, and also cloud applications, big data analytics, intelligent medicine, and actually all types of computing. To enable these key technologies, then we need to make our semiconductor devices with higher performance, low power, and smaller area, less cost. And we have three main directions to achieve this PPA goal. The first one is more with continuous scaling, such as nanosheet, transistor, EUV lithography, or the backside power delivered interconnect. And the second, beyond CMOS with new devices, such as silicon carbide, and all these compound semiconductors, which has higher electron mobility to improve the operating speed and also power density. And third, more and more with the heterogeneous integration to pack multiple components with a low cost into a whole system to achieve the PPA goal. So we have the different options to achieve this performance, power, and PPA goal. For more and more options, we can leverage the transistor patterning and interconnect technology to achieve our goal for transistor. For example, currently we use the FinFET. Soon we'll use the nanosheet, and even the complementary fab already introduced for production by TSMC last month, and ICC. And for patterning, currently we use EUV together with multiple patterning. We can achieve the better goal. And for interconnect, we have a backside power delivery and even optical interconnect, also just announced by TSMC last month to be included by 2025. The economic advantage of more scaling are getting smaller and smaller because of very high manufacturing costs due to the EUV and advanced transistors. Making more and more the trends are more obvious. The heterogeneous integration with 3D stacking is promising with a better system PPA and also the form factor and also the functionality. However, there's a few significant issues before enjoying the ride, including the capacity, yield, heat, interconnect cost, mechanical stress, etc. Advanced packaging has become more critical than ever. Dr. Yao Chang in 2016 mentioned that the info package is the key for TSMC to beat the sensor for Apple's exclusive A10 chip orders. Yeah. And since last year, the CoWAS advanced technology used in NVIDIA advanced high-end GPU server has suffered very significant shortage, production shortage. Yeah. So we can feel the importance of this important advanced packaging technologies. That you can see with the shortage, it really affects the development of AI technology and also the high performance computing. Yeah. Here is a schematic diagram of heterogeneous integration with various components reproduced from Georgia Tech's report. Yeah. You can see this system consists of optical components, the digital analog chips, and vision amends and sensors interconnect with TSV and also the waveguides. Yeah. For this kind of complex systems, we need to consider the multiple physics domain issues, not only in the physical design, but also the electrical, thermal, mechanical, and optical effects all together. Yeah. There are significant interactions among these different physical domains. For example, the thermal affects the mental conductivity, generating IR drop, even affect the timing, and also the wavelength of light, and also the stress. On the other hand, the IR drop generates an additional heat, and the stress induces the transistor degradation. So there's some interactions we need to consider for our advanced packaging design. We have multiple options for heterogeneous integration, including the CoWAS and also the info package, silicon interposer, and silicon which dies triplet, and even more advanced monolithic 3D ICs. Here is the list, the whole combination of TSMC's 3D fabric, including the info, CoWAS, and also the SOIC. And for each technology, it also considered, it also have detailed features for different applications. Yeah. And last month at the ICC, Dr. Kevin Chang mentioned that by year 2025, TSMC will include the silicon photonics into its advanced technology. Like IPRS and IRBS technology roadmap, experts from the globe work together to come up with the HI roadmap since 2015 with the latest version in 2023. So you can see that from the technology roadmap, it covers all aspects of technology and even applications we need for advancing heterogeneous integration. For example, here the chip integration, silicon photonics, co-design issues, and thermal management, and even the 3D interconnects. Yeah. So for physical design challenges and solutions, as I mentioned earlier, here I don't mean, even with a solution, I don't mean we have to resolve all these challenges. So here I would like to present you the many open research opportunities. Yeah. Here I give a list of hard issues for each physics domain. For example, for system-level design, we need to consider system-level modeling, simulation, and power performance thermal cost analysis. And for physical design, the tools for 3D partitioning, formatting, placement, routing, all need to be reinvented. Yeah. And we need to consider the chip, pack, or co-design. Yeah. And for electrical effects, we need to consider the the power signal integrity, and even eye prevention. Yeah. And also the spatial plating through holes. I'll mention I will introduce to you in more detail later. Yeah. And for thermal effect, we will consider the stacking interconnect for system, the thermal analysis, and jaw, eating, etc. And now we have very significant mechanical effects with the warpage and also the straits. Yeah. And the optical issue even come into the picture. Yeah, we need to consider optical routing, thermal aware, device placement, and even electrical and optical core design. Yeah. Let me elaborate on this some of the critical issues. Yeah. For 3D system level partitioning, we need to partition means logic and memory into multiple dies with the different technologies for PPA optimization. Then by different technology, I mean the device sizes and design rule change with different die assignment. Yeah. So it's not just the min cut partitioning. So it will create some chicken and egg problem. Yeah. Should we design the partition first based on the current size, or should we decide on the size first and then do the partitioning? So, yeah. So we need to consider the process technology for multiple dies and corresponding interconnect via bound parameters for the overall cost optimization. Yeah. And here I also want to introduce the cost physics domain for planning problem. Yeah. We need to integrate the dies into an advanced package, which might suffer the very severe electrical, thermal, and mechanical effects like stress, warpage, substrate noise, etc. Yeah. Here I show you an example. Here it shows the plating through hole PTH connecting the bond to a ball. With this kind of hole, it could induce a very severe EMI problem. So there is a very special design rule for this kind of devices. Here show you the ball label, the plating. Yeah, you can see that. This is a plating hole, this is a non-plating hole. Yeah. For this kind of problem, we need to plan the PTH rulings, yeah, by determining their locations, aspirations of these holes for better the bond, PTH, and ball routing. Yeah. I haven't seen any publication along this line yet. Yeah. And mechanical issue becomes very significant. Yeah. Here we published a paper at TEC 22 warpage aware opening because Dr. Peter Ho, the senior vice president of TSMC, told us that the TSMC really need warpage aware opener, which is lacking in the design flow. Yeah. The warpage effect is induced because due to the mismatch in coefficients of thermal expansion between two materials, such as the die and interposer. Yeah. So this kind of mismatch will cause thermal mechanical stress, and thus the warpage. Yeah, we never handled in our EDA area before that. Yeah. So for this work, our warpage model is based on Sotier theory. Yeah. And we use our TCG floor plan representation to get the optimized floor plan and then verify with NSYS tool. Yeah. And for die, as I mentioned earlier, dies integrate into a package could be factored with different technology nodes. So the block sizes are changed dynamically due to the die assignment. This is the chicken egg problem I mentioned earlier. So should we decide on the block size first or do the die assignment first? Yeah, this creates really a headache for us. Yeah. So at the ICCAD last year, the synaptics formulated the complex problem with the 3D face placement. So you can see the objective is to minimize the scoring function with the total wall length and also the terminal cost connecting the different dies. So we are so lucky to, I have to show this. We are so lucky to win this contest. Let me show you our technology. Which will to be published at the DEC this year. Yeah. So basically, based on this board, mid-size 3D global placement and die assignment, macro-regularizing, terminal insertion, terminal cell core optimization, standard cell regularization, and detailed placement. I don't have time to go into detail, but I'll show you the main technology. So we formulate this problem as an unconstrained optimized problem with the objectives for wall length, terminal cost, and also density. Yeah. We use our weighted average model for wall length optimization and apply the E-phase 3D for density control. Yeah. So we optimize the object function using a gradient descent for this unconstrained optimization problem. Yeah. By increasing the lambda multiplier gradually to reduce the density to find the desired macro and the standard cell locations. Yeah. Here is the key to smoothly assign the dies. Yeah. We relax the discrete assignment variable and use a sigmoid function to achieve a smooth strip transition. For example, if a cell A is placed at the top die, then its width would be 3. But if placed at the bottom die, then the width becomes 5. So for the die assignment, we need a smooth transition between the top die and the bottom die. So we leverage the sigmoid function here, stand for the height and also other parameters. Yeah. So here is a demo for our 3D mid-size global placement. Yeah. So you can see the assignment to the top die and bottom die actually very smooth. Yeah. So this is quite the key that we can get a good result. So this is the final results. Yeah. Yeah. And for routing, modern packages require very high performance connections among triplets through a multi-layer redistribution layer, RDL, redistribution layer, RDL, interposer for substrates. Yeah. The RDL is used to connect the I/O pad to the bound pad. Yeah. To achieve better quality and also to provide more area for I/O, higher performance interconnections, better the system integrity, etc. The rising complexity requires any absolute angle routing to consider the complex design rules, including there's stacking rules, irregular vias, and inline staggered bounds, etc. And for ideal routing, we can classify into two types based on the routing styles, free assignment routing and also pre-assignment routing. Yeah. For free assignment routing, each bound pad can be connected to any I/O pad. Okay, yeah. But for pre-assignment routing, the connection between the I/O pad and bound pad are predefined. So you can see the pre-assignment routing actually imposes more constraints, so they become harder. Yeah. Okay. Yeah. Okay. Yeah. So with the routing style is a routing this is the routing style, and we also have a different architectures, per video I/O and also the area I/O. For video I/O, the I/O pad actually placed along the chip boundary, and for area I/O, the I/O pad placed anywhere in the chip. So we got this quadrant. Yeah. Here for each quadrant, the related published work listed here with P technology shown. Yeah. So we have a 4 quadrant. And actually, for existing work, we can even unify the pre-assignment and also the pre-assignment nets, because for many designs, it does consist some pre-assignment net and also the pre-assignment net. So we can also see this kind of unified work. So about 20 years ago, I believe we presented the first work on peripheral I/O pre-assignment RDL routing based on a network flow formulation. And recently, we work on the area I/O pre-assignment and also the unified pre-assignment and pre-assignment work based on the monolith diagram to control the full network and also apply the dynamic programming to solve this problem. Yeah. The network flow formulation is very useful for modeling the resource assignment problem. However, it has a key limitation. We can control only the total flow, not the individual flow at some specific age or not. Okay? Yeah. So for free assignment routing, we don't have a restriction for the assignment of which the bound pair to pick, right? So the network flow becomes very popular for this type of problem. So the most existing work actually based on the mean cost maximum flow formulation. So you can see that for this chip, we can divide into 4 regions, right? For each region, we can construct the full network like this, and then we can apply the mean cost maximum flow to resolve this problem for global routing. And here shows the routing result for peripheral I/O and pre-assignment routing. Yeah. And for pre-assignment routing, we need to consider the specific assignment between the I/O paths and the bound paths. So the traditional maximum flow formation cannot apply to this problem because we cannot control either on the individual flow for a specific node or edges. Yeah. However, we can utilize the regular free chip structure to achieve a better solution. Yeah. For this kind of regular structure, it's really remind us of the dynamic programming. Dynamic programming works best for the linearly ordered objects that cannot be rearranged. That's a keyword I use in my algorithm class for my students. Okay. Yeah. So for all the problems with this kind of spatial structure, we should smell the dynamic programming. For example, the string, calculating string, and the matrix in the chain, and also the points on the circle. These are all exhibits this kind of regularity. Okay, so we can apply the BP for the pre-assignment routing. Yeah. So for the pre-assignment routing, before I introduce this solution, I would like to share a real story. Okay. At that 10 banquet, well, for younger researchers, younger friends, we did have a very huge tech banquet in the good old days. Yeah. At the banquet, Dr. Wabasi of NEC Vice President, with a lot of wine and drunken eyes, he asked me, Yao Wen, why are Taiwanese so friendly to Japanese? Big question. Okay. I replied, well, I could give you the 100 reasons. Reason number 1, number 2, blah, blah, blah. But most importantly, there's a Da Vinci Code between Japan and Taiwan. So I grabbed a napkin and wrote down the country name, Japan and Taiwan, JPAM, PAIWAN. Then you look at the country name, there's called the longest common subsequence. So it's a way to measure the similarity between two DNAs. So the similarity is actually more than 50%. So we are destined to be very good friends. Okay? Yeah. Yeah. Okay, so we united back last year. Yeah. Now Wagaba Bastian becomes a professor at the University of Tokyo. Yeah. Yeah, actually he becomes more charming without hair. Don't tell him, I don't care. Okay? Yeah. So I would like to apply this kind of dynamic program technology to the assignment routing. Okay? Yeah. We can minimize the detours with this kind of technology by using long common subsequence. So if you can see if we have a well-ordered I/O paths and also the bump paths, right? By getting the long comma subsequence, that means I reduce the detours. So if I have a longer comma subsequence, then I don't need to have a detour for these two red connections. And for the ring, for the bump path, we can also apply the maximum planar subset of poles, to compute the non-intersecting poles, which also means the non-detours. So with this two dynamic token technology, we can solve this problem with a very good quality. So basically, we can identify the feasible sequence for I/O path first, and apply the long comma subsequence, and then we decompose the chip into rings of a bump path and route from the inner rings to outer rings, and then we keep applying the MPSC between the two adjacent rings to get the result. Okay. So with this kind of technology, we can achieve over 100 times the speed up than previous IOP formulation with a better quality. Okay, So here shows the demo with this kind of technology for global placement. And in this demo, it also shows our detailed logging process. I believe, it's a detailed logging process. I'll skip this part. Okay, And for modern package routing, we need to consider we need to apply any up-to the angle routing to maximize the flexibility. So it's desirable to plan the T drop angles to maximize the routing, because the local T drop angles could affect the faraway connections. So I haven't seen any publication on this topic yet. Okay. Lastly, we published I believe so the first angle router with multiple RDRs. For any angle routing, it can fix for example the rate spacing violation here, and we apply the denominator triangle to have the tile partitioning. Then for each tile we can model the intra and also the inter capacity to generate routing guides. Then we can apply the dynamic programming. Okay, with this sequence, dynamic programming based SS point adjustment to route multiple net simultaneously. So to achieve the best published results. And here shows an example from TSMC. Okay, containing all types of routing constraints. For their needs. Okay. So look at this list carefully. Starting from the top left, the differential pair for phase matching, and the PTH placement with shielding, and also the length matching for skew, and also the match the escape orders for bus loading, and there's constraint regions, and also the inline staggered structures for different bump pad handle, and also the bump breakdown. There are also some other issues, not listed in this slides. For example, irregular views, maximum density for reliability, etc. So the research life in visual design is really good. Really good. Okay. But if work at TSMC is really hectic. So different culture, different needs. And for PCB placement and routing, the key problem is we encounter very irregular shaped 3D components. Even with a T-SYNC, and under the T-SYNC, you can even place other devices. Never seen in our physical design problem before. Okay, And for routing, we need to consider signal power from the wires of different widths, more than 100 times the difference. Okay, so here's some general consideration for PCB placement routing: component orientations, wire widths, also dynamic spacing rules. with a different clustering. The spacing rule, are different. Yeah. So if I see with the market, I was trying to be the closer to market. But if the Zhongyi, then I'll keep away from it. So that's happening in our real life now. So another chicken and egg.
What if I want to be close to him?
I have to make some mistake. Yeah, so you can see so market pose an even harder problem for the solve, right? Yeah. Okay. Yeah, and it becomes more desirable to have a chip package for the core design. So you can see that with the core design, we can achieve a much better results. Yeah. Here I'll give you an example of a chip package for the core design published many years ago. Yeah. So please look at this signal started from the I/O buffer all the way to the port and the PCB. Yeah. So we allow the signal from the I/O buffer to a pre-chip bound through with the RDA routing, and then the BGA board with the package routing. Yeah. Here we're ready for PCB connections. And then we need to apply the escape routing to the boundary and the area routing to the destination. Okay, this is a whole process. So for this core design problem, we presented a ball-driven lambda-shaped core design flow, starting from the immersed escape routing in PCB, and also the ball bound mapping in the package table, and also the package-aware I/O placement on chip. And then we'll perform the bound reassignment and RDA rerouting in the package. And then finally, the escape rerouting in the PCB to coordinate the work to get the data quality. Okay? Yeah. Okay. Should be low enough, right? Don't even need a microphone. Okay. Yeah. I just mentioned TSMC has announced to integrate the silicon photonic component into its advanced package by 2025. There's a presentation from ISCC last month. Yeah, actually earlier. IBM. Okay. Yeah. With the co-packaged optics. At yesterday's keynote, Lucia told us that they expect we have 1,000 watt power consumption for the next generation NVIDIA GPU server, GPU server. Okay. Well, you ask me, I would say they won't. They won't. With the TSMC and also the co-packaged optics, we can reduce the power very significantly. What the examples are shown in the top. They can reduce the power from 2,400 watts to about 850 watts. And I believe the power consumption will be improved gradually. Yeah. And yeah. So for the optical design, it's quite different from electrical. Yeah. For a signal, here shows electric optical architecture. For an electrical signal, we can convert it into the optical signal and then transmit the signal through the optical waveguides. Yeah. You can transmit the multiple signal together with the different color of light, like the red, the orange, green, etc. All simultaneously. And then we can convert back to electrical signal. So for light, related to for the optical routing, well, it allows the connection in any directions and even signal crossing. So with a higher bandwidth, low power, and faster speed. Yeah. So and the signal transmit through the waveguide. They can be clustered together, as I mentioned, red, orange, green, etc. So there is also induced some signal clustering products.
And overall, our goal is to minimize the transmission loss and also the wavelength power. Yeah. Okay. Yeah. So another significant issue is the optical electrical core design. Because for optical components, they are very sensitive to heat. Okay. Yeah. So we need to generate a global optical waveguide to optimize the thermal impact and not protection of wireless. Here shows us three scenarios. Yeah. The first one is routing without the optical layer, which might cause a significant routing protections here. And then here is a scenario with unwise optical waveguide through the heated region. So they will cause some problem with the optical device like micro ring like resonator. Yeah. And with the OE the routing core design, we can have a desired solution like this one. Yeah. So this shows the nature of this kind of problem. Yeah. And for AI, there's much research work for the AI-based visual design. So I won't elaborate on this topic. However, I want to stress that AI and EDA are actually complementary to each other. They should help each other to achieve the PPA goal. For example, the AI technology, we all know that have already reshaped our EDA community landscape. Let me give you a quick example. At Tech 22, our AI empowered person for work among the NPK, Maxta, and NTU. Really improved the chip design, MediaTek stated chip. Yeah. And on the other hand, our EDA technology can help AI system design and enable the AI applications. Here's another example from the Tech 21. For an AI chip with a convolution network, it consists of very dense interconnections between the two layers of neurons, right? So with this kind of dense connections, even the leading commercial tool cannot resolve this problem well. So our tools tend to rescue by reinventing the EDA methodology. So that's why Synopsys decided to acquire our company last year. So the AI for EDA and the EDA for AI, I believe, bring a significant research opportunity and also stars. Yeah. Okay? Yeah. So finally, my concluding remarks. We have discussed the many visual design challenges. In my opinion, for design the EDA challenges, we can explore these kind of challenges from four directions: high complexity, multiple objectives, and greater the heterogeneity, and also the new technologies. Yeah. Let me take a 3D picture as an example. These challenges have already reshaped the present problem. The modern placement becomes a top because of the high complexity with say the 100 million of objects next. And besides the traditional visual design metrics like the wireless, we also need to consider the post-species constraints like the orbit, thermal, etc. Yeah. And the component sizes are quite different. Quite different. We typically encounter the mixed cell height, the mixed size placement with 100K the bit macros, with 100 million smaller standard cell of multiple cell height. Yeah. And new technology will, of course, introduce many other challenges like AI, like the new bonding integration technology in HI. Yeah. So in my opinion, besides the technology, in my opinion, design and EDA collaboration is very even more critical. Yeah, they should act complementary to each other to help to achieve the PPA goal. Yeah. However, there's a cultural difference, between chip design and board design. The chip designer typically encounter the very large scale, regular, homogeneous component with a uniform design rules. In contrast, the board designers need to handle the small scale, irregular, heterogeneously component and with very complex design rules. Yeah. So they have a different mindset, even with the same challenge. So what should I say? Well, chip designers are from Mars, board designers are from Venus. Yeah. So how should we deal with that? Well, my suggestion is don't try to change them. Okay? Yeah. It's our job to change how we communicate, react, respond to our partners. Yeah. After years of collaboration with them. Okay? Yeah. This is my experience. Okay? So in conclusion, we have multiple approaches to achieving the PPA holy grail with more, and beyond CMOS technologies. And we have multiple complementary options to achieve the HI target. Yeah. In my opinion, to achieve the ultimate PPA goal, we really need an ecosystem to bring all experts from the different physics domain all together. Together, we can go far. Yeah. And well, our EDA is definitely essential. Okay. Now, it's my belief that. Okay, it's my belief that the technology challenge will not limit our progress because our human imagination can bring us to the endless frontier. So to conclude my talk, I would like to share the Einstein's most inspiring quote: "The human spirit must prevail over technology." Thank you. Yeah.
Okay, as usual, very informative and also very inspired. So, but I really missed Yao Wen's presentation. When he offered the class, he almost overtime. Like the presentation today. So I think we only have I think we can only take almost 2 questions. Okay, any questions?
I think I still within the time bound.
Yeah, but, okay, Faisal.
Yeah. So will you get another ticket? Really? You already another second. Can trade the
Thanks, Professor Chang, for your distinguished talk. I have a question regarding AI for EDA. So recently, just like yesterday, Professor Beiyu has given the presentation about large language modeling for EDA, and he proposed 3 potential applications: the script generation, debugging variable generation, etc. But my question is that it seems that we may borrow some ideas from the advancement of AI community and apply these ideas to our community, to EDA community. But do this, so how do you see that this kind of a trend? Because I see that these years we have a lot of papers discussing these kind of AI applications for EDA published by that ASICAD. So how do you view this problem?
Okay,
and do they really give the revolutionary change to our community? Thank you.
Okay. Now there's a very huge, broad question, very great questions. Okay. Yeah. First, I have to be politically right. Okay. For EDA designers, I would consider the artificial intelligence another kind of aided tools. Okay. AI alone, I don't believe that AI alone can resolve all the questions, like the claim from the Nature Placement paper. That one is really the okay. Yeah. Okay. Yeah. That's my my general views. But as I mentioned, EDA and AI should be complementary to each other. Since we have a more mature AI technology, we better leverage the AI technology to help our EDA development and vice versa. Yeah.
For example, the AI, community, they do have a very good image processing and data analytics techniques, right? So I believe all the EDA problem, particularly associated with image and data. For AI, we can leverage this kind of technology to at least improve the efficiency. Yeah. Something like that. For example, for training place, and leverage the image, the analogy to have the placement, right? And for many IR job analysis work, we typically leverage the big data analytics to have faster processing of the huge number of parameters, yeah, to have our EDA efficiency and also quality, yeah. So in general, I believe they should be complementary, but not the trend in the AI area that they want to be the some critical statements like AI can do anything, okay? So that's why we have the nature people also our products, yeah. Okay. And I'm also really surprised that that's. I should not make it. Okay. I'll get in trouble.
My question is very safe, don't worry about it. So I
Yeah,
have
that's
a
okay.
technical question that
Yeah.
in about 20 years ago when we worked on 3D IC, we used
Yeah,
TSVs, right, for both signal and also thermal conduction.
Yes.
Here, do you still need the routing to take away the heat, or
Yes.
is this taken
Yeah.
care of by some other way?
Yes, for modern advanced packaging, the thermal issue becomes even more significant. Yeah, it's even cause some other effect like mechanical stress and warpage, etc. Yeah, but we still follow I would say the similar philosophy from the TSV with more advanced technology to make the interconnection smaller and smaller. So with that.
So then how you route, how you place, you should consider thermal
Yeah.
as well,
Yeah.
not just the wiring. Because
Yeah, there are some
yeah, you want to take the heat away, right?
yeah, there are many options to handle the heat problem. But the heating problem is still the basic thing. So if you want to invest in the markets, right, try to look for the thermal prevention or thermal handling companies. Yeah, I know that there's a company in Taiwan. Their market price, their markets are increased even bigger than NVIDIA. Working on the thermal. So for thermal, we can use different materials and different cooling techniques. And of course, our EDA technology also come to help, yeah, with different to place the heated component close to the heating some the borders, the boundary of the chip. This kind of technology also apply, yeah. But many more focus actually on the materials to reduce the heat. Yeah, thank you so much.
Okay, I think there's no break for next section, you know. Yeah, so I think we really need to thank Professor Yao Wen Chang for the wonderful talk.